Okay, so when's our test? Wednesday.
I thought you were actually going to say today.
I'm not that creative. Yeah, exactly. Tony Weinbeck, the guy who was in here the other day and wrote "Don't listen to anything I say" on the board, he did an April Fool's test. I think it was like a quiz, and he handed it out, and the problems got just increasingly more ridiculous. They didn't even make any sense. It was just like, imagine you're like in a parallel universe where the gravity actually like produces mass at this rate, and like. No, it's a pretty standard quiz. Okay, and the topics for the exam are everything up through linkages. So none of the rotating coordinate system stuff. And so today or Monday, if you have any questions about linkages or anything related to the test, I'd be happy to spend time answering those. Other than that, we're just going to keep going with the new material. Anybody have any questions related to the test or linkage problems or anything like that?
I don't have any specific
Yeah.
example, but can you go through one with the constraint equations?
Yeah. Let's go through a linkage problem. Can't hurt. What?
The Wednesday's problem that you gave us without any angles.
I'll give you a new one, and I'll put an angle on there. So then it's twice the... Okay, so... Oh, I know which one you mean. So yeah, it looked like this, right?
Considering the angle is just theta. Yeah, that one.
Yeah. So these should be 20 degrees. But that's not the example. Okay, so let's say we have this member connected to the ground at a 45-degree angle, and we'll make this 1 meter. And then this member, let's make it 1/2 meter. And it's horizontal. And let's say, so we'll call this 1, this member 2, A, B, and call that point P. Actually, let's forget that. Skip point P. That's easy. And let's say the mass of member 1 is 10 kilograms. The mass of member 2 is 5 kilograms. And there's an external couple acting on member 1 of 500 Newton meters. And we want to calculate the angular accelerations of the two bodies. Okay, so they're connected by pin joints. The only external loads are the weight and this one external couple. So what's going to happen with this linkage? So first, member one. Step one, does member one have a fixed point? Okay, so 2, the moment of inertia, the fixed point is A. So the moment of inertia is 1/12 times the mass times the length squared plus the parallel axis theorem. The mass is 10. The distance from the center of mass to the fixed point, what's that? 0.5. And so you get, let's see, this is 2.5 plus 0.833. So I think that's 3.33334. That's round off error. Okay, and this is kilogram meters squared. And then a free body diagram. Oh, I didn't say it, but let's say that at this instant, omega 1 is equal to omega 2 is equal to 0. So that'll just clean up the calculations a little bit. It doesn't change the concepts. Well, if I say on a quiz that there's an angular velocity, then I would not recommend that you do that. But of course you can. Right, exactly. That's always the catch. You always can. So what loads do we have acting? Weight. So 98.1. Yep. What else? Yep. RA, and one more. The couple, yeah. Is that 500? Is that what I said?
How does that couple act since it isn't in the joint? Is it acting over the page?
It could be, yes, it's acting out of the page based on the direction that it's going. But the kind of thing that could apply that is like it could be connected to a motor or something, or it could be built into this joint, applying that. Bring up the joint. Oh, and I think the easiest place to put the origin would be here. Okay, so at the origin, that F12 is acting. The about point has to be at the pin, so the about point is at negative 0.7071, negative 0.7071. So the row vector is positive 0.7071, positive 0.7071. The force vector is F12x and y. And so you get 0.7071 F12y minus 0.7071 F12x. And then at the about point, at A, the location is negative 0.7071, negative 0.7071. That's also the about point. So the row vector is 0. The force vector is RAX, RAY, and that doesn't produce a moment. And then you have the weight. Chris, how would you figure out where the weight's applied?
Probably the midpoint.
Yeah. And to get the midpoint, average those two. So that's at negative 0.3535, negative 0.3535. The about point stays the same. So subtract and you get positive 0.3535, positive 0.3535. It's always the vector from the about point to the point of interest. And the weight is 0, negative 98.1. And what do you get for that? Negative 34.68. And then the last one we have is the couple. We don't care about any of that stuff, and that's just a positive 500. Step 5, do we need Newton's second law? No, because there's a fixed point. So then the moment equation says negative 0.7071 F12x plus 0.7071 F12y. 500 minus 34.68, 465.32. And that's equal to the moment of inertia, which was 3.33 times alpha 1. So that gives us our first equation for our system, negative 0.7071 F12x plus 0.7071 F12y minus 3.333. I'm going to just keep putting a different number of 3's in this every time. Just to demonstrate my contempt for significant figures. And no. And that's equal to negative 465.32. And the variables, we have 3 of them. That's the F12 vector and alpha 1. And now we'll go on to body 2. So that's this horizontal member. Does this one have a fixed point? And so we have to take the moment of inertia about the center of mass. So that's 1/12 times the mass times the length squared. What do you get for that? Okay. What the? Okay, kilogram meters squared. And then the free body diagram, we have the weight. And then the force on 2 by 1, so that's negative F12. And that's all. Negative F12 acts at the origin. The about point is negative, that has to be at the center of mass, so that's at negative 0.250. So the row vector is positive 0.250. Force vector is negative F12x, negative F12y. And so the moment is negative 0.25 F12y.
I thought that was at the origin. Yeah.
The force is at the origin.
So the about point, the about point would be 0, 0. Could we put the about point? Oh no.
Right, because there's no fixed point, so the about point has to be at the center of mass. Too late. Okay, so then the weight force is at negative 0.250. The about point is negative 0.250. And so the row vector, the weight x at the about point, so that's 0. Force vector is negative 49.05, and no moment. Do we need Newton's second law for this one? Yes. So negative F12x, negative F12y, plus 0, negative 49.05 is equal to, the mass is 5, times the acceleration of the center of mass of member 2. So I'll call that A2. And that gives equations for our system 2, which says negative F12x minus 5A2x is equal to 0. And 3, which says negative F12y minus 5A2y is equal to positive 49.05. And then 6 is the moment equation. And that says negative 0.25 F12y is equal to 0.104 alpha 2. So that gives our fourth equation for the system that says negative 0.25 F12y minus 0.104 alpha 2 is equal to 0. And now for the variables, before we had F12 and alpha 1, now we also have added the acceleration of the center of mass of 2 and alpha 2. So that's 2, 4, 5, 6. So after Newton's laws, we have 4 equations, 6 variables. And so we need two constraint equations. And so those constraint equations are going to come from the fact that the acceleration of B according to member 1 is equal to the acceleration of B according to member 2. So I'll write it like this. Acceleration of B according to 1 is equal to the acceleration of B according to 2. Okay, so member 1. Do we need relative motion for this? No, because member 1 has that fixed point. So the acceleration of B is just equal to the watermelon equation. We don't have any angular velocity. So this is 0, 0, alpha 1, crossed with, what's the R vector for member 1? Yeah, positive 0.7071, positive 0.7071, because it always goes from the point that you're treating as fixed, that fixed center of the rotation, to the point of interest. And so you get negative 0.7071 alpha 1, and then positive 0.7071 alpha 1. Any questions about that one? And then member 2, the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. So why do we need relative motion for this one and we didn't for the first one? There's no fixed point, yeah. And why does why are we doing it sort of like, if you think of the relative motion equation always includes this intermediate stop, this intermediate choice that we're going to do something relative to, and then, so why did we choose the center of mass of 2 for that intermediate stop? We always do it this way. Why?
Isn't it like it has to be the bound point? Like center mass is the bound point, and we want to consider the point that we're interested in.
So actually, this equation would hold for any, instead of center of mass of 2, we could choose any point on that body we wanted. The benefit of choosing the center of mass, and it's a major benefit, is that we've already been forced to define a variable that represents the acceleration of the center of mass of 2. So it'd be a nightmare. Like we could do it, we could use our relative motion equation according to a point a quarter of the way across, but then we'd have to come up with a new expression for, okay.
And then make markers.
So, yeah, right. So that relative motion equation holds for anything. We're choosing the center of mass as our intermediate point because we already have defined that variable. And we did that because we have to for Newton's second law. Okay, so this is A2. The acceleration of B relative to the center of mass of 2 is equal to alpha 2 cross R2 plus omega 2 cross quantity omega 2 cross R2. This goes away because there's no angular velocity. So this is equal to 0, 0, alpha 2. And then what's the r vector in this case? So actually it goes from the center of mass, because that's our, so you're always, whenever you're using circular motion for one of these relative motion terms, whatever you're doing it relative to, that's always going to be your start point for r. So we're going from the center of mass of 2 to b. Okay? So that's going to be positive 0.25, 0, 0. And so you get 0, positive 0.25, alpha 2, 0. And so the final expression for AB relative to the ground is 0, 0.25, alpha 2, 0, plus A2x, A2y, 0. And so now put those two together. So we want the acceleration of B relative to, not relative. The acceleration of B according to member 1 is equal to the acceleration of B according to member 2. So that says, what was it, negative, darn it, I forgot to look. Okay, negative 0.7071 alpha 1, and then this one was positive. 0.7071 alpha 1 is equal to 0, 0.25 alpha 2 plus A2x, A2y. And so for our system of equations, the fifth equation says negative 0.7071 alpha 1 minus A2x is equal to 0. And the sixth equation says 0.7071 alpha 1 minus 0.25 alpha 2 minus A2y is equal to 0. So now we have 6 equations, 6 variables, and we can solve that. Okay? Any questions about that? All right, let's do the quiz.